So most of the work that I'm presenting can be found in these two archive preprint. So since I'm from the other hemisphere, that's the map of the world that I like to look at it. So I come from Australia, from the east, from Brisbane, and I work at Quantum Optics and Information Lab. And this work is specifically funded by Center for Quantum Computation and Communication Technology. So if you ever come to Brisbane, there is a lot of good nature to enjoy. But if you are not very fan of nature, there is always good science to enjoy. So you can visit our website and see what is there for you. All right, so this work is a collaboration between obviously Griffith University, University of Queensland, and Tim Brought's group, and also the National Institute of Standard and Technology in the US. So I particularly acknowledge the PhD student, now a postdoc, Luis, who has done a lot of these works. Right. So we have been hearing a lot about quantum communication and its challenges, but I want to start with probably the most simple, but yet probably most challenging task in quantum communication. So you have two parties, Alice and Bob. They want to share some sort of message or entanglement via photons, and this is a challenging task because we have loss. So on average, if you send 100 photons on a 100-kilometer fiber, only one of them survives. And that is bad because it takes forever to get the message. And also, you really don't know if the photon is genuinely lost. There might be an eavesdropper sitting in your channel and getting your photons, but you think actually that's a genuine loss. That's a problem. So in classical information or classical communication, what we do, we use an amplifier. We have a weak signal. We send it to an amplifier, set the gain, and then we get a strong signal. And that's all good. But in quantum, things are a bit different. I bring this paragraph from Tim Rao's paper. It says that it is well known when a linear or phase-sensitive amplifier acting on a quantum optical field, or more generally on a harmonic oscillator, must introduce noise. So that's bad. But it gives some hope to us. Like it says, we show that a non-deterministic but heralded noiseless linear amplification is possible. Right. What does it say? So no-cloning theorem says that if you have an unknown quantum state, you cannot clone it perfectly. And by perfect, I mean with fidelity 1 and deterministically, right? So you cannot do that in quantum mechanics. In other words, if you have a coherent state alpha, there is no physical operation that can act on alpha and gives you G alpha, where G is larger than 1, G is your gain, right? This is not possible. But what is possible is that you can sometimes get an amplified state that's basically working probabilistically. And this p-value is an important factor, which I come back to it again. But for now, if we can do this probabilistic amplifier in a heralded manner, which means that there is a signal that says to you, okay, the amplification is done, that still can be a very useful tool for quantum communication. So our focus would be on this heralded probabilistic amplifier. So if we look at inside this box, we'll get something like this. There would be a coherent state going through a 2R port beam splitter, and then we have these rails, which it says that each rail has less than one photon on average, right? And then we have these NLA units, or noiseless linear amplification units. And then we have again, the reverse beam splitter, and then we have the amplified state and heralding and vacuum. But this scheme has a few problems. First, the probability of success of the P that I mentioned already depends exponentially on the probability of success of each of these NLA units. So, and because the average photon here is less than 1, you need many of these. Therefore, this the whole thing, basically the probability of success of the whole thing fails very fast and, as I said, fails exponentially. So that's one problem in general. The scheme is not very good. The second one, imagine you have a scheme. There are some schemes you only need one of these units, one NLA unit, but there's still the probability of success of these units is pretty low. And I show you why we should improve the probability of success of this. So in the first task that I am showing here, I'm focusing on a distillation task, entanglement distillation task for one of those NLA unit and show how to improve the probability of success of that NLA unit. Back to my first slide. So I have Alice and Bob again. They want to share entanglement, but there is some sort of loss here, which is described by this transmittivity eta, right? So if I don't do nothing, my entanglement is somehow blurry and probably is not very useful. But just to give you a sense of how the mathematics of these things work, so basically how it works, you have Alice side, we have two modes, A and B. So you generate a single rail entanglement between these two with this beam splitter, and then send it through the loss, which is again modeled by another beam splitter, as I said, with transmittivity eta, and then B or Bob receives the part of the entangled state which is shared between mode A and B. So the general state looks like something like this. You can see the entanglement and also the factors based on these like tau and eta value. So that's all good. But as I said, the do nothing protocol is not very good. So then I go back to the NLA unit that I showed to you before, the one NLA unit. So generally speaking, what happens here that Alice sends her state again, we have the loss, but then Bob also uses some sort of resources state or ancilla state, right? And then what happens, you have this interference, quantum interference here, and if there's a photon and detection in either of these detectors, you have entanglement distillation between Alice and Bob. So that is how that one unit NLA works. And that's based on what is called generalized quantum scissor. So now again, a bit of more mathematics. Again, Alice have the modes A and B. We have the entanglement generated here, loss here again, transmittivity eta. But Bob now this time also have an entangled state, and then we have this detection. If there is one click in either C or B, then we have entanglement sharing, entanglement shared, and this still between A and D. But crucial point here is that so only Alice's state going through this loss. Bob's state doesn't go through any loss. And it seems to me like that. So Bob is holding this relay or heralding station to itself. And only Alice sending the state towards Bob, right? Okay, so this work and realization of this has been done like almost 15 years ago. And then Tim Rolfe and his group asked this question: what happens if we move that heralding station to the middle, right? So now Alice's state going through the square root of eta, Bob's state going through the square root of eta, and then again, if we have a click either in one of these detectors, we have the entanglement distillation. So a fair question to ask, I guess. A bit of math again, same idea here, but this time a square root of eta, same idea here, but now notice that we have also loss here, and then detection in either C or B. We have entanglement between A and D. That's all good, but then interestingly, it appears that if you do that, moving the relay station into the middle, you would get a increase in the probability of success. In both cases, I'll explain what is X, but in both cases for X10, the NLA at the middle or halfway they call it is better than NLA at both ends. Same here for another X value. So basically what by just simply moving this heralding station to the middle, you can increase the probability of success of the whole scheme, right? So X value is here. So X is that although this is a heralded scheme, you get a photon, you say, all right, the amplification has been successful, but still there is loss in the system. There is a chance you get a heralding, but you don't get anything in the output, right? Because of the loss. So the X value tells us number of time. If you get a heralded, you get one photon in the output divided by when you get vacuum in the output, and they call it the purity. But this is such an important factor, because even though you get a heralding and you think, okay, it is successful, but there's always a chance that you get nothing in your output, right? So now we thought, okay, that's an interesting idea. Let's do an experiment. And we designed the experiment. So experiment is relatively simple in terms of the design and implementation. So we have this PDC source, and then we have two photon generated, separated by this, like, basically polarization beam split. And one thing you should know, that I showed you the entanglement in the previous slide. That's a single rail entanglement, but we use basically polarization or dual rail encoding to mimic the entanglement, right? So then you have the entanglement, like Alice's side, Bob's side, and then you have these interferometers to control the amount of loss that each of these state go through. And then you have the central interference, and this is the heralding station, and that's the output. So these experiments generally are demanding in terms of amount of loss that you can tolerate in the system, right? For example, here, to do this experiment, we have to design and realize a source with efficiency larger than 80%. And what that means, that if you have a SPDC source, you get one photon. The probability to get another photon, the other photon, should be larger than 80%, right? So that is, and this is directly connected to the X value that I already explained to you, right? And the other thing is that because I'm doing heralding on single photons, any noise, any dark count in the system would appear to be a heralding signal, but that is why you have to decrease your dark count and noise to a very low level to be successful in this experiment. So now I did the experiment, there's some data. So in the left side, I show you the probability of success of the original protocol, NLA at bob ends. So, and then NLA in the middle. So you see, obviously the probability of success has been improved. But more importantly, when you compare these two results with the direct transmission, what is direct transmission? If I have a 100-kilometer fiber, I just send a photon towards in that fiber, then you see at some point actually the NLA in the middle beat the direct transmission bound. And this is important because I'm not using any repeater. This is a repeaterless, basically beating the direct transmission bound in the transmission of photon. So that tiny improvement might not convince you yet, but when you look at the purity of the state, you see that if you use just a fiber, the purity of the state, the number of time that you get vacuum, exponentially decays. But then using NLA, you can keep it at least floating in around a constant line. And that is why we eventually need to use some sort of repeater or repeaterless scheme to beat these bounds. So that's the kind of the first part of my talk. And I showed you how to improve the probability of success of these NLA units if you only are dealing with uh, less than one photon on average. But what happens if you want to amplify a genuine high energy state, like a coherent state? As I said, this is not very practical. So there has been some effort during the last decade or so to do something like that, but there has been either the output state was too noisy, or the experimental hardware couldn't tolerate the amount of loss, like including this paper by um, um, Xanadu team, that they used a like Borealis boson sampling machine, but they couldn't show the genuine amplification because of the amount of loss in the system. So there has been like mostly a theory challenge to come up with an idea to do something like this, but in a more experimental friendly way. So then, as I said, going beyond low energy state. So then again, Tim Rolfe came up with this idea that we can use quantum Fourier transform, right? So quantum Fourier transform here, and this there is a lot more information in this paper, but I just bring up the two photon case here for you. So you have the two photon ancilla here, then psi, which is a at most is the two photon state Fox state. So then you have the Fourier transform, and then you have the heralding station. So based on the pattern of this heralding station, you either get two photon, one photon here, or like zero here, or vice versa, any combination. Then you get the amplified state, which would be something like this. Like you see that now I have that obviously the vacuum, the amplification of the one photon term, and also the amplification of the two photon term. So that is what I'm trying to do here, amplifying a state that has basically more photons, or is a higher energy state. So as I said, there are different patterns for heralding. I go back again. You can have two here, one zero here, or two here, zero here. So based on what pattern you get, what heralding pattern you get, you need to implement a local phase to get the final state. Right. So this is the experimental setup again. We use a SPDC source this time again, but we pump it hard to get some two photon terms in our input. Then we separate it. This is basically realizing the Fourier transform and the whole scheme. And this is the heralding detectors, right? So we use like nanowires to get a high efficiency detection, and then this is the overlap at the end. And I show why we need this overlap at the end, right? Okay. Okay. So now we build the amplifier. We want to test it, right? Okay. So testing this amplifier, like we use a relatively simple idea. So you have this imbalanced Mach-Zehnder interferometer. This gamma value is basically um, controls the splitting ratio of this beam splitter, right? Imagine you set the splitting ratio of this beam splitter in a way that you get a very weak signal here and very strong signal here. But then if you amplify this and get a balanced state between two arms, the only way that you get a high visibility interference here is that if this amplifier coherently amplified your state, right? So that's the only way you can get a high visibility fringe here. So that is the way we test the performance of this amplifier, right? Okay. So for example, we set the value to 0.1, and then like obviously 90 to 1, 90 to 10 splitting ratio. And then to do that, like you do calculation to have a balanced state between two arms, you need to set your gain value to 3, which if you talk about intensity, it's like 81 intensity gain. And then you look at the fringes, right? And then, as I said, you have different heralding patterns. So this is the fringes for one of the heralding patterns. So the visibility is quite impressive. This is for another heralding pattern, less impressive, and then again less impressive. So we think we understand why the fringes have different visibility, and that's mainly because of the loss that affects one fringe and doesn't affect the other fringe. But if you look at the paper, there is a kind of an extensive explanation of different losses and their effect on the visibility of the fringes. So that's okay. So we have done the amplification, and we have tested the coherence of this amplifier, right, with this interference pattern. Other thing we can do with this kind of amplifiers is that we can measure the gain directly. Again, so you have the state, you have this beam splitter, which is basically works. It's splitting ratio is controlled by parameter tau. And then if you measure your intensity here and then compare it directly with the amplified state, at least for this like term two photon term, then you can compare the gain, because this two photon term is amplified in intensity by G4, in amplitude by G2, and then you can compare the value of intensity here before and after, and then you have the G4 value, right? That is how we measure the gain of the amplifier. So this is, as I said, rho out to rho in. It should be proportional to G4, and this is the theory line. But we know there is a normalization factor which depends on the splitting ratio of that beam splitter, and also the gain of the amplifier. So we have tested for different value. So tau equal to 0.1, but if we increase the loss basically, then tau equal to 0.05. Basically, if I go back, the state that is passing the bismuth is smaller and smaller. And it seems to me that when the state is weaker, the amplification works better. And there's a reason for that. The reason for that, because at most I have two photon, right? At most I have two photon. So basically my amplification is saturated to two photon. It is not a like n photon state. It is only a two photon, and that is why you see this saturation. But at least at the small value it is in agreement with the theoretical line. But more importantly here is that the gain value, which is to best of my knowledge, has been done for the first time for two photon state, and you can see the gain here. So in the second part of my talk, I showed that you actually can do high energy state amplification, although it's challenging, but you can do it. So I still have some time. I thought maybe I should show you something fun. This is, I was visiting my family in Iran, and then the war started. And this is my escape route from somewhere here in the west of Iran to Ankara, to Istanbul. So this was supposed to take me 2 hours, but it took me almost 5 days. And I brought up this slide to not give you a political message, but to make you feel bad if you haven't listened to my talk. Thank you.
Thank you. We have time for questions, comments. Are there any?
Everybody understand?
Yes, we have question over there.
Thank you so much for this nice talk and well presented. So I have two quick questions. First is, in effect, are we tweaking the coefficients of the states involved in the superposition, like C1, C2, and so on?
Sorry,
And
can you repeat again?
so do we have any control on the value or the amplitude of the coefficients of the states involved, like C1, C2, for example, to increase the probability, the success probability?
Yeah.
Yeah. And second, can we do this for higher dimensional states, for example, 1-1, amplifying the signal on two modes, or I don't know.
Okay, so the first question is that if you have any control in this, right? So the direct control you have on like C2, because you are using some sort of beam splitter here, then you can control at least C2. But obviously, because it is a probabilistic, then like sometimes one photon pass, sometimes two photon pass, and you can calculate that, right? So that's the first. Can I do it for higher number of modes? Yes, you can do it, and there is a scheme in the theory paper here, but it is very challenging. Yeah.
Thank you.
No.
Yeah. Other questions? Yes.
Hi, thanks for a very interesting talk. Do you see a similar relation to the noise amplification that you see in Like, I mean, quantum limited amplifier with the coherent state can amplify the signal, can like increase the number of photons, but increase the noise. Do you see like similar relation with the post-selection probabilities? So like you're able to increase, but you're
Uh, this one is supposed to not do that. So even this one, if you wanted to do anything meaningful, you have to basically increase the number of these NLA units to infinity to have a good amplified state without noise. But this scheme supposed to not introduce noise and work for a high energy state without adding noise.
but then you're post-selecting on a specific outcome,
Yes,
and
but
this thing
that's
decreases.
the truncation. So if I had more photon, I had more like output heralding ports, then I would truncate until the end term, right? So that's what is called like quantum scissor. You truncate the state to the end term, but before that, it should be fine.
Okay, I happily continue the conversation
Okay,
other,
all
as I
right.
know I have
Okay,
other stuff to ask.
all right.
Okay. More questions? No? If no, let us thank Farzad again.
Thank you.
And